This is a secret film containing restricted data. Gentlemen, the purpose of this meeting is to bring you up to date on the ANP program. During the 3 years since the last filmed report was made, a good many changes have taken place in the program. This briefing will cover that 3-year period, 1956 through 1958. For briefing purposes, we have broken this program into 2 sections. The manned program, which will be covered in this first film, and the unmanned, or Pluto, Rover, and SNAP programs, which will be covered in a separate film. This, then, will be the Aircraft Nuclear Propulsion Status Report for 1958. The Aircraft Nuclear Propulsion Program was established in 1950 as a result of feasibility studies conducted under the NEPA and Lexington projects. General Kern was given command of the project in the Atomic Energy Commission, which was responsible for reactor development, and in the Air Force's Air Research and Development Command, which was responsible for engine and airframe development. During the next few years, the main objective of the program was the development of design information which would permit evaluation on a firm basis of flight feasibility and of the effort required to achieve such flight. In 1955, the Air Force established a requirement for a strategic bomber of extremely long range and capable of a supersonic dash to the target at high altitude. As a result of this requirement, the Aircraft Nuclear Propulsion Program was oriented toward the development of such an aircraft, Weapon System 125A. Work was immediately started and continued steadily until major material problems resulted in reduced thrust-to-weight ratios, indicating an adequate supersonic dash radius was not feasible. This performance loss resulted in a reappraisal of the entire Weapon System 125A program in the fall of 1956. Subsequently, a new program was begun with major emphasis placed solely on the development of a nuclear propulsion system. This program was placed under a dual-agency Aircraft Nuclear Propulsion Office with General Kern in charge. In March of 1958, a presidential directive approved a program development objective of a militarily useful aircraft. A short time later, in order to maintain airborne alert and high payload capabilities, penetration requirements were reduced from high altitude to low altitude and from supersonic to high subsonic. Low altitude also offers greater probability of survival during penetration. This new approach was known as the CANAL concept. Under this new CANAL concept, the nuclear-powered aircraft would patrol at high altitude for long periods of time. If necessary, the patrolling nuclear aircraft could proceed directly to pre-designated missile release points, launch their long-range missiles, and then drop to a low level to perform low-altitude evasive pattern penetration at near sonic speeds to either perform reconnaissance or deliver a lay-down weapon against hard or hidden targets. Studies indicated that high subsonic penetration speeds at low altitude would provide maximum mission protection. The difficulties of low-altitude radar detection, as well as recent high-altitude nuclear bomb tests in the Pacific, have indicated the advisability of low-altitude penetration. These missions could be performed without benefit of foreign bases and at reduced global operating cost. Besides the major propulsion program for manned aircraft, other associated areas under investigation include airframe, shielding, radiation effects, life sciences, and safety. In 1957, the ANP program was also expanded to take in the 3 additional nuclear projects designated Pluto, Rover, and SNAP, mentioned before. First, let's look at the manned aircraft program and the two different propulsion methods. They are General Electric's direct or air-cooled system and Pratt & Whitney's indirect or liquid metal-cooled system. Of the two, the direct cycle system promised early flight capability and was selected for the major propulsion effort. In the GE system, a solid fuel element, air-cooled nuclear reactor was located between twin engines. Air coming into the engine is compressed by the compressor blades, flows through the hot reactor where it is heated and conversely cools the reactor, and then passes through the turbines and the engine exhaust nozzle to produce thrust. This design makes it possible to modify the reactor core without disturbing the remainder of the system. Heat transfer reactor experiment number 1, utilizing this principle, was conducted in January of 1956 at the National Reactor Test Station in Idaho. Inside the initial engine test facility, the reactor was brought to criticality, and the engine switched from chemical burning heat to run entirely on reactor heat. The operation was successful, with temperatures of 1400 degrees achieved at the turbine inlet. In the fall of 1957, this same reactor engine setup was used for a series of Heater 2 tests. The only major change was in the active reactor core, which was modified by removing the 7 center fuel tubes to form an octagonal hole. By this means, various solid moderators and fuel element materials could be inserted within the core and tested. Altogether, 3 inserts were tested. The first used a clad hydride zirconium moderator. The second, an all-ceramic insert made up of layers of beryllium oxide tubes with a beryllium oxide moderator. Incidentally, during this test, a record interior temperature of more than 2,700 degrees Fahrenheit was reached. And the third insert successfully tested an unclad hydride zirconium moderator. A fourth test was then conducted to obtain experimental data on fission product releases. The airflow to one element was deliberately restricted to the point where the fuel element melted. Data from this and similar experiments are used in determining operational criteria so that nuclear operations will not result in a hazard to the public. A special high-power reactor system was then constructed and designated HTRE number 3. It incorporated flight-type reactor controls and a flight-type reactor shield. This model illustrates HTRE number 3, the first flight-type horizontal 33-megawatt solid moderated reactor. This was a significant stride forward in propulsion development. The power plant simulated flight-type geometry and structure. It was expected to provide valuable shielding data as well as solid moderator performance data. The initial engine test facilities were also modified for the HTRE number 3 tests. For example, a 400-foot tunnel was constructed to provide a shielded roadway beyond any possible contaminated area. This permitted changing shifts without shutting down the reactor, and in the event of reactor failure, the entire structure could be evacuated in seconds. Late in 1958, HTRE number 3 was moved to the initial engine test facility for its first test run. During a low-power test experiment to determine heating rates in the various components of the system, an error in electrical circuitry caused the reactor to exceed the design power level. Consequently, damage to the fuel cartridges and some moderator blocks occurred. Valuable data, however, were obtained during the operation and from the incident itself. As an example, the inherent safety of the reactor was demonstrated when the change in geometry resulted in an automatic shutdown of the reactor. These HTR number 3 experiments were expected to proceed in 1959. A short distance from the IET, a flight engine test facility was under construction. Here, full-scale propulsion tests will be conducted, possibly with a nuclear propulsion system mounted on an airframe. This facility was to be ready for use in 1959. Other GE facilities at the Idaho test site include the Shield Test Pool facilities, where the swimming pool reactor was to be ready for operation in 1959, and the newly completed low-power test facility, which provides for critical experiments on simulated reactor core configurations and fuel loading of actual cores. While these operations were going on in Idaho, GE's Evandale facilities, located near Cincinnati, Ohio, continued work on the direct cycle propulsion system, which was designated XMA-1. This model illustrates how the XMA-1 system consisted of two X211 turbojet engines with a reactor fitted between them. Reactor control rods were located in the forward section of the reactor. This cross-section view shows how compressed air would enter and leave the reactor through a series of wavy ducts. This design allowed the passage of air, but trapped the straight-line nuclear radiation. A full-scale mock-up of the XMA-1 propulsion system was also constructed, with the simulated reactor heat source in the center. A comparison with the conventional J79 chemical engine gives some idea of the X211 engine in size and power. For instance, the J79 weighs 3,400 pounds. The new X211, 15,700 pounds. J79 has 17 stages of compressor stators, 6 of these stages being variable. The X211 has 16 stages, all variable. J79 sea level thrust with afterburner, 15,600 pounds. The X211, 34,400 pounds. It should also be noted that while it will operate on chemical fuel, the X211 was designed and built and is at its most efficient under nuclear power. 4 of these engines had been successfully tested with chemical fuel only in a large test cell which had covered air intakes and tall exhaust stacks. This test setup closely simulated the XMA-1 reactor engine combination with an X211 engine on the left and a dummy engine on the right. The reactor was simulated by a center heat chamber which produced temperatures, pressures, and fluctuations simulating those of the reactor. This engine, the third, was operated for 30 hours under chemical fuel at low 1100 degrees turbine temperatures. Eventually, it will be run at 1700 degrees. The first twin engine running was scheduled for the third quarter of 1959. Concurrently, work on flight reactor development was also being conducted in General Electric's Evandale Aircraft Nuclear Propulsion Department. Here, nuclear power generation was being simulated in fuel element testing by the use of induction heating. An intensive research program was also being conducted to develop and evaluate high-temperature metallic fuel element materials. New chromium-based alloys of improved strength and workability were being developed. In a similar way, moderator materials were being developed to improve hydrogen retention and metallurgical stability at elevated temperatures. Other materials were also being examined for possible use in the reactor core. For example, hydrolysis tests were being conducted on beryllium oxide fuel elements under maximum temperature conditions. In 1958, however, a chromium fuel element with a clad hydrided zirconium yttrium alloy moderator looked promising for the tactical reactor core. Schedules called for the first direct cycle nuclear propulsion system ground test in the spring of 1961. The entire General Electric program cannot, of course, be covered here, but those were the major propulsion program highlights. The other propulsion system under investigation is Pratt & Whitney's liquid metal cooled indirect cycle system. As I mentioned earlier, at the termination of the Weapon System 125A program, the decision was made to concentrate on General Electric's air-cooled direct cycle system for early flight. As a result, the Pratt & Whitney indirect cycle system was reoriented toward long-range objectives, causing severe cutbacks in early development effort. For example, the work on the circulating fuel reactor propulsion system, which was a joint Oak Ridge Pratt & Whitney program, was first cut back, then canceled. This included the aircraft reactor test at Oak Ridge and all conversion work on the Pratt & Whitney J91 chemical engine. At the present time, Pratt & Whitney is concentrating on a high-performance solid-fuel liquid metal-cooled reactor with all-nuclear supersonic flight potential. This This system also operates by using a solid fuel reactor to supply heat to various type power plants. But in this case, the reactor is liquid metal cooled with a coolant circulating through radiators placed inside the engines, where it transfers its heat to the air leaving the engine compressors. The liquid metal coolant under consideration is lithium-7. If, as in early models, this coolant is sodium, a secondary loop is needed with an intermediate heat exchanger. This is because sodium carries appreciable amounts of radiation from the reactor core, while lithium does not. For this reason, using lithium, the secondary circuit would not be necessary if an oxidation-resistant radiator compatible with lithium can be developed. The indirect cycle work is being accomplished at the Air Force's recently completed Connecticut Aircraft Nuclear Engine Laboratory near Middletown, Connecticut. The first phase of the reoriented program consists of reactor research and component development. Primary emphasis at the present time centers around the development of a suitable liquid metal coolant and the necessary containment materials. As part of this study, molten lithium has been circulated through forced convection loops. The loop tubing is made of various materials to test corrosion and mass transport effects. In this instance, the containing material is a columbium alloy clad on the air side with stainless steel to protect the alloy from oxidation. Other forced convection loops are operated inside huge pressure tanks in which the air has been replaced with an inert gas to prevent oxidation by outside air during the tests. Temperatures of 2,000 degrees Fahrenheit have been sustained for 250 hours. More than 25,000 hours of these studies have shown that columbium alloys give the most promise for reactor structures because of their high temperature strength and resistance to mass transport with lithium. Of prime importance at Pratt & Whitney is the construction of a forced convection loop for testing fuel element assemblies in nuclear test reactors. The reactor test loop resembles a miniature liquid-cooled reactor, except that it contains a subcritical amount of fuel. In preparation for testing in Idaho's engineering test reactor, a full-scale loop was operated under non-nuclear conditions. A 1,000 kilowatt oil furnace was constructed to supply the heat which in the test reactor will be provided by a 5-inch fuel element. It was necessary to place the loop high up above the furnace to provide the proper heat and circulation environment. The reactor test loop was scheduled for operation in the engineering test reactor at Idaho during 1959. Other components of the indirect cycle system were also undergoing intensive testing. In this instance, data are being gathered on a small-scale model of the heat radiator. Molten sodium-potassium alloy, NaK, is passed through the radiator, making it red hot, as it will be in the engine. And, as will happen in flight, a blast of compressed air is loosed on the radiator, subjecting it to extreme thermal shock. This same effect will occur in flight when the pilot varies the airflow with the controls. Quarter-section radiators were scheduled to be tested under various simulated flight conditions in the newly constructed $4 million pilot radiator laboratory. Other CANAL facilities include a pump turbine laboratory for testing full-scale liquid metal pumps and pump components, a heat exchange laboratory for testing liquid metal to liquid metal heat exchangers, an air laboratory for testing radiator turning vanes and other air components, a special hazards facility for determining liquid metal air and liquid metal water reactions, a nuclear physics laboratory for conducting reactor critical experiments, and a general laboratory for chemical and metallurgical research. The present indirect cycle research and development phase will continue through mid-1959. By that time, it is estimated that the program will have progressed to the point where the fabrication of an experimental aircraft reactor will be considered by the AEC. As you can see, this is a vast propulsion system program, with both General Electric and Pratt & Whitney conducting extensive investigations. As of the last of 1958, we expected to have a direct cycle nuclear system in ground operation by mid-1961. Now, this isn't the entire picture, of course. Closely connected to the propulsion program is the question of shielding. As you may recall, shielding for the nuclear aircraft has been divided, with a shadow shield around the reactor and additional shielding around the crew compartment. This arrangement subjects all parts of the plane to radiation, but allows a slimmer, more aerodynamic configuration with an earlier flight potential. Actually, shielding investigation can be broken into two sections, experimental and theoretical. One of the greatest contributors to experimental work has been Convair, a division of General Dynamics at their Fort Worth plant. As you recall, late in 1955, and working with Oak Ridge National Laboratory, they converted a B-36 into a nuclear test airplane to investigate the split shield concept. This was not a nuclear-powered airplane. Its engines were the conventional chemically fueled engines of the B-36, but it did carry an operating water-cooled 1-megawatt reactor in the Bombay area. Following the split shield concept, the reactor was shielded, with shielding around the crew compartment also. A series of in-flight radiation tests demonstrated the feasibility of this concept and produced information regarding the detrimental effect of decreasing air density at higher altitudes. The flights also provided the first substantial data regarding the effects of radiation on aircraft structures. Following the flight tests, the reactor shield and the crew shield were transported to Oak Ridge, where they were positioned in the tower facility. The reactor was then operated, continuing the study of shielding effectiveness. By 1958, many new shielding materials were being investigated, including reactor shielding materials such as lithium hydride, beryllium oxide, tungsten alloys, and depleted uranium. While Oak Ridge continued to be the leader in theoretical studies and experimental testing, material testing was also going on at other facilities. For example, the Battelle Memorial Institute swimming pool reactor was being used to conduct shielding tests. General Electric's shielding activity was soon to be stepped up with the completion of the previously mentioned shield test pool facilities. Theoretically speaking, shielding computations based on these experiments have produced encouraging results. For example, given a weight, it was now possible to predict the resultant dosage to the crew within allowable limits. This program may be summed up by saying that shielding materials were pretty well set, although fabrication procedures were something of a problem. We could, however, fly a first development aircraft with existing shielding designs, but more in-flight data would be needed for an operational aircraft. Much the same can be said for the radiation effects program. Radiation concern has been confined to fast neutrons and gamma rays and their deteriorating effect on organic materials, as well as their effect on metals under stress. The effect of induced radioactivity for prolonged periods after exposure and radiation effects on electrical components and electrical fields were also being investigated. To supply this critical information, a series of dynamic tests have been conducted at Convair's ground test reactor facility near Fort Worth. Complete subsystems were mounted on platforms and instrumented. The systems were then remotely moved into place near the reactor, where they were operated within the high flux field. It is significant to note that during these tests, failure due to nuclear radiation occurred in 46% of all systems. Lockheed Aircraft's newly constructed 10-megawatt radiation effects reactor provides the means of dynamically testing complete systems in a high-flux field. After the systems are mounted on a flat car, they are moved into position near the reactor. The critical reactor is then raised to the proper height. Thus, the complete system can be operated while under irradiation. As many as 6 systems may be operated here simultaneously. In addition, the newly constructed Air Force Nuclear Engineering Test Facility at Wright Air Development Center may soon provide the information necessary to develop radiation-resistant materials. The Reduced Radiation Effects Program was of necessity a limited effort. However, it was the belief of personnel working in this area and in shielding that while the present state of the art would not support a full-scale strategic weapon system, it would support a developmental prototype nuclear-powered aircraft. Research efforts in the life sciences were directly linked with progress in other fields, such as shielding, irradiation, and the planned use of strategic aircraft. As a result of the program to date, enough data had been obtained to ensure the safety of the crew with present shielding. At this time, it was considered possible for a crew to fly for relatively prolonged periods without dangerous effects. The safety analysis program was also being conducted on a somewhat limited scale. Part of this study included radiation release tests conducted in Idaho. Here, radioactive material was deliberately released, along with smoke for plotting purposes, to investigate the effects of a nuclear aircraft crash and reactor burnup. Results of these and weather effects studies indicated that nuclear considerations create no undue hazard to civilian populations if adequate operational controls are exercised. Of extreme significance to the program was the 1958 presidential decision to bypass a purely test bed or demonstration aircraft and to concentrate on the development of a useful military weapon. At the close of 1958, two companies, Lockheed and Convair, were in competition for this development contract. Both had long been associated with the ANP project. Lockheed Aircraft's program was begun in the spring of 1951 with a nuclear propulsion study. In 1955, as part of the Weapon System 125A program, they were asked to design an airframe for Pratt & Whitney's closed-cycle propulsion system. During this design period, Lockheed also conducted studies of a combination tug-tow strategic system called Blackjack. After the launching of Russia's Sputnik, several quick-fly or test-bed designs were investigated, but these were canceled by the development aircraft decision. By the end of 1958, Lockheed had submitted their proposal for a developmental aircraft based on applicability to the current CANAL concept. In addition, Lockheed was conducting limited studies of a manned aircraft employing both Pratt & Whitney turbojet and ramjet nuclear propulsion systems. These studies presented designs of advanced aircraft having high-altitude, supersonic flight capabilities. Convair has experienced a somewhat similar development since they also began a study program early in 1951. Similarly, in 1955, also on the Weapon System 125A program, they were teamed with General Electric and the direct cycle propulsion system. Following original program requirements, they first developed their Model 25 concept. Then came a design called Tarpon, followed by the GE propulsion system testbed, which was a version of Tarpon, and the Model 54 design for the Camel development airplane competition, which was completed by the end of 1958. Early in 1959, and in time to be included here, the decision was made as a result of the previously mentioned competition to award the development airplane design contract to Convair when the decision was made to go ahead. This aircraft would be powered by the GE direct cycle propulsion system. Design work on this aircraft began. As you can see, this is a huge program, and it's impossible for us to cover every area of development. However, the GE direct cycle propulsion system was currently undergoing dynamic component testing. The Pratt & Whitney indirect cycle system was in an intensive developmental stage, and an experimental reactor was forecast to be ready for operation in 1963. The various support programs, shielding radiation effects, radiobiology and safety, were keeping pace with the planned major system delivery schedules with the objective of a nuclear flight in 1964. ANP progress in the development of nuclear propulsion and power systems for unmanned weapon systems will be covered in a separate film. At the successful conclusion of these programs, we will possess a means of delivering huge payloads over unlimited ranges with a minimum of foreign commitments. That, and a knowledge of nuclear power application second to none. Thank you, gentlemen.